Dr. Elham will be presenting us a 35-minute workshop on natural language processing.
Thank you so much, Monica, for the introduction. So I share my screen to start. Just one moment. I guess you can see my screen, yeah? Okay, yeah. That's great. So let's share this in the chat. Just one moment. Okay. So anyone can follow while I'm going through that Google Column. So today, first, I talk about the NLP pipeline, and then today I cover like text pre-processing and text normalization steps in NLP pipeline, and then after me, Muhammad will join this workshop and then tell us a little bit about word and sentence embedding. So today, the idea of this NLP pipeline that we have a raw text as an input of this pipeline. So when you have a raw text, the next step is clean that text. Why we need to clean that text? Because we have some unwanted words, we have some noise, we have some characters that in the text that you don't want to have it. For example, if you catch some tweets and you want to analyze it, so you need to remove some emojis, you need to remove some hashtags or some characters that you don't want to. And then after that, you need to normalize it. So normalization means that you need to make it clean in one way, it's just like before, but it's something that you want to like a lemmatization or stemming step that I explained last week. So it's more that you normalize your text. And then after that, when it's clean and normalized, that's the next step that you can transfer these texts to vectors, which is a numerical value. Because any model, you know that any machine learning model cannot understand text. They only can understand numbers. So we need to transfer text always to some vectors, and it can be word embedding. So it's like you can take one word and then transfer it to a vector, or you can take one sentence as a whole sentence and transfer it to a vector. So there are different possibilities. And then after that, you build up your model, train your model, test your model. And then the result of this, a pipeline can be some graphs, some classification of text, or some other like analysis over text that you want to know which part is talking about, for example, one topic or not. So in the first cell, I put some libraries. You can run it, but if you don't have that library installed in your computer, you just can easily put pip install. For example, I didn't have word to numbers, and then it just easily you can put that, and then you can install that library easily, and you can follow. So about text processing or text cleaning, I will tell you that how you can remove symbols, how you can remove Unicodes, and remove extra byte space, convert accent characters to ASCII characters, expand contractions, or treatment for numbers. So I put one variable as text. You can put anything you want. So this is something that I put that you can put any text to try different functions for each step to see that how it's changed. So first I talk about removing symbols. So symbols, I put symbols in one variable. It can be anything. So you can add more symbols like add, and, or anything that you don't want. If you don't want a parenthesis, you can add that as well. And then you see here, I put like an example that we have symbols, you know, in a sentence, you have like a hashtag. I can add, for example, ads, because I recently add that ad, so I can, and then you can see like a new sentence. There's no symbols in it. So the other one is removing Unicode. So what is that? Is like we have some ASCII characters, but if there are some other characters that you can see here, you see here that there are some characters that is not defined in Latin, for example. We can easily try that, and then you know, using some text encode and then decode it, you can remove those. As you can see here, that I put one ASCII that is one number that is not related to ASCII of Latin characters. And you see here that after applying this function, I remove it. So I can see one question that what do you do if a word have a spelling mistake? So that's a good question. It depends on the data set. So you will see it like later that we do lemmatization and stemming. So, and then we can find some roots of one word. And if you use that, if there is a one mistake like typo a little bit, then you can transfer it to stemming. But if there is some spelling mistake, still we can take it as a one word, and we don't care about like this is a mistake or not. So I continue here, and you see here when I remove that word, so you see here that I have a white space. So in the next step, I tell you that how you can remove some white space that you don't want. And I put an example. You see here that I use a join and then split it and then join again. So in that sense, you can easily remove some white space. You see here that I put an example with white space, and then I can clean it. And also in the last example, you know, I put it in text clean, and then I remove white space at text clean, and I print it, and you see that there's no extra white space here. We convert accent characters. So how we do that? For example, you have cafe, and you don't want some accent characters. How you can do that? You need to use the library called Unicode. Unidecode that you can decode like the characters in a sentence, and then transfer it to Latin, or you transfer it to English characters. Expand contraction, what does that mean? So it means that when you have a word don't, so you want to change it to do not. So you want to like make it clean to understand and understand the sentence better. And then when you tokenize it, you can better understand, because when you tokenize it, this is understand it as one word, but you don't know that, okay, this is do with not, which is like a negative meaning. So here is another function that I use for contraction. So this is a function that contraction that fix. You can apply, for example, here in one sentence that I have don't, and then when I apply it, you see that this don't, it changed to do not. what we can do with numbers. So it depends on your data set, and it depends that do you really need those numbers or not? Sometimes it is important that we have the numbers. We can sometimes there's for example, in your text, there's some quantitative value or quantity inside the sentences that you're really want to make a decision based on that. So for that one, so you really need to take that numbers, but sometimes numbers doesn't say anything in your purpose or your results, so you can easily remove that. One way that you can transfer like a number, but in a numeric form. For example, 7 as a word, you can transfer it to 7 as number. So here with that function that I put here, that you see that 3 cups of coffee, and then I transfer it to 3 cups of coffee. There is another function that I didn't use here. That's possible that you transfer, you know, it's like a opposite that you have like a number, and you want to transfer, for example, 3 as a numeric value, you want to transfer it as 3 as a word value. And that is another possibility that I didn't put it here, but you can easily search and find it. And here is a function that, you know, like I have a number 7, and then I don't want that number. So I can easily say that, please, I use re and sub. This means that substitute that if you find some digit, dash slash d means that digit. So it means that any time that you find digit, substitute that digit with nothing. And then you can see here. And this function, we use it like very often. And this is something that anytime that you want to substitute some like values, some patterns with something else in your text, and you want to clean it, and you can easily do it. So for text normalization, I already talked about like removing stop words and lemmatization, but I told you a little bit again here. But one other thing that you can transfer all of your words to lowercase. And then I tell you that how it is important. So at first I tell you that how you can do it, just using the function char.lower, which is like you can transfer easily. That I put an example here with capital, and then you see here that is all in lowercase. So for stop word, I already talked about the stop words. You see here the stop words, list of stop words, and then I put a sentence here. The idea of giving computers blah blah blah, and then I want to remove the stop words. Anytime that you want to remove the stop words, you need to first tokenize those sentences as using word tokenization, and then you say that okay, if it's not. Only put that again inside the list if it's not a stop word. But you see here there, which is like a stop word, I still have it. So this means that I have it because I didn't change it to lowercase. So if I easily here, you know, like change here to convert lowercase. And then first is converting the text to lowercase, then word tokenization, and then I check if there is any stop words, and then I remove it. And you see here, you see that I don't have the here. So it's really important that first we transfer it to lowercase and then remove the stop word. Lemmatization, I already explained. And this is really easy that you see here that I have here, and then kept, I find the root of that word. So it means that if I have different combination of like keep, kept, or other kind of combination of like a word keep, then you can transfer it, or keeping, it can be changed to keep. This means that we can have have a numerical value for that word by using lemmatization. For the assignment, I asked you to put all these processes in order, and you can define a function. So this function can be text pre-processing, and you put all these steps together. So it means that the input can be a text and the output can be clean and also normalized text data. So it's like in a one way. So it's not like you do with each step. Like in one step, you can define a function and then you put other function inside. And this is, I think, very easy, but the solution is in that reference. So the question I have, does the function contraction only work for English language? I didn't try for other language, but I don't think that it's only be usable for English language. I didn't try it, honestly. So, but from I can say that it's a high possibility that it works with other language, because most of the libraries in NLP is written for English and also for other language as well. And especially for common language like French or Spanish. I have the same question, can the function work in Arabic? Yeah, some function really work for Arabic, but you know, it doesn't, you see that like these words, like for a computer, it doesn't mean anything, just some characters, but you give some meaning to them. And Mo will explain to you that how you can give meaning to some word for a machine to understand that this is delicious and this is cafe. What is the synonym of one word to the other? And so it doesn't matter that it's in Arabic or in other language, it's just some characters, but you give the meaning to these words. So I pass to Mo to continue.
Yes.
Thank you.
All right. Thank you very much, Ilham. Just before starting, can I have an idea of how much time left there is? Tim, Monica, just to see how quickly I have to go. Hello?
Yep, you would have till 3:55.
Okay.
Oh, sorry.
Okay, I might need to go over by a few minutes, so I apologize in advance.
That's okay.
For this. I'll do my best. Okay, so hello everyone. I'm gonna share my screen. Should be able to see it. Can you guys see it?
Yep.
Yep, awesome. All right, so word and sentence embeddings. All right, so as Ilham was mentioning, there's a few steps that we need to do before starting building a model and training it. And specifically, why do we need embeddings? Well, the thing is, we need them because we need to be able to turn our textual data into numbers in some way, such that the models that we're going to train are going to be able to process them. So what is the intuition behind vector semantics and word embedding? So the idea is that words that occur in similar contexts tend to have the same meaning. And when we say similar context, we are talking about words that appear nearby each other in a specific text. So embeddings are going to leverage this idea by representing the meaning of words as vector. So in practice, what does this mean? First of all, let's talk about words as vector. So the word vectors, they're usually based on a co-occurrence matrix. And the word vectors, essentially, they're representation of the meaning of a word in a certain document. So there are two means of co-occurrence matrix, the term document matrix and the term matrix. So let's go over them. First of all, we have the term document matrix. So in the table that you see in blue, basically, we have an example where for the columns, we basically have plays by Shakespeare, and the rows correspond to the vocabulary that spans the entire plays. So basically all the words that appear in every play. And each cell value is going to correspond to the number of times a certain word is going to appear in a certain document. So for example, battle, we can see that it appears 7 times in the document, in the play Julius Caesar. Fool is going to appear 36 times in As You Like It. Now, documents, we can represent them already as count vectors. So here the documents are the columns, and they can be represented as vector of words. So every column is going to correspond to a distribution of words over the entire vocabulary. So remember that here we only show 4 words, part of that vocabulary, to make it easier to visualize it. However, there are thousands and thousands of words in the vocabulary. But each column can be represented as a vector of words where each value corresponds to the number of times a certain word appears in that specific document. And we can actually plot them. So here we plot it in 2 dimensions. So that means we only plot along the word battle and the word fool. And remember, each word is represented by the number of occurrences of that word in a specific document. And what we can already see is that when we represent them as vectors, these 2 documents, for example, Henry V and Julius Caesar, are much closer to each other. And As You Like It and Twelfth Night are also much closer to each other than they are to the others. And that basically means that those documents are similar to each other. So the way we represent vectors, we represent them in a way such that the ones that are close to each other, that share common meaning, are close to each other when we plot them. Now we're talking about document vectors. Well, we can do the same for words as count vectors. So here it's the same table. The only difference is that we're going to look at the vectors as rows and not columns. So basically each row is a numerical representation of a word based on its number of occurrences in each document. So if I take battle, for example, if I want to represent it as a vector, I'm going to take the number of times it appears across the different documents that we have. And here, so the words are the targets that we want, the vectors, the embeddings that we want to create, and the context is the documents in which the different words appear. So we were talking about term documents. So we had basically the words as a function of the documents. We can use a term-term matrix. So in that case, both the rows and the columns are labeled by the words corresponding to the entire vocabulary. So in that case, each cell value is going to correspond to the number of times the row. So we'll look at the row, the target, and the column, context. So those are the row and the column are both words. How many times they co-occur in the same context in a certain document. And how do we do this? So here's an example. So we're going to take a window of words. And that basically means for every target word, basically we're going to take, for example, 4 words prior that main word, cherry, and 4 words after that main word. And that is going to form our window of words. And basically to count the number of occurrences, number of times that word appear in a certain context, well, we're going to look, for example, at pie. We see here that that pie appears once next to cherry. That means we're going to update the value in this table, right, on the row cherry and the column pie. We're going to update it we're going to increase it by 1. If we take strawberry, for example, it's the same thing. We take the 4 previous words and the 4 words that follow it. We see that pie appears twice. That means basically for strawberry, the row strawberry and the column pie, we would have to update it. We would have to increase it by 2. And the same way we had a notion of similarity between documents when we were representing them as vectors, as a plot, we can already see here that there are similarities between different word vectors. Remember that each row is a word vector. If we look at digital information, we see that they have a lot of occurrences, co-occurrences with the words computer and data. This tells us basically that semantically, these words are close to each other. They share the same context and their meaning are very close to each other. It is the same thing for cherry and strawberry. If you look at pie and sugar, the number of occurrences with those words is very high when it's not the case for digital information. So here is the notion of similarity and meaning when we represent words as vectors. So this is just a representation. Remember, we have for digital and for information, when we plot them based on the data and the computer dimensions, so the number of occurrences, the co-occurrences with data and computer, we see that they are going in the same direction. This tells us they are similar to each other. Now, what we saw with the co-occurrence matrices is that we were using every time the raw frequencies. So that means the naive count of words in the different documents. So this is not the best measure when we want to associate words, because some words might appear very, very frequently in many different documents. So there's somewhat a paradox here. So there are words that occur nearby very frequently, and those words are more important than the words that only appear a few times. However, words that appear too frequently, they're not important. For example, a word like the or good that appears in every document is not interesting to us. It doesn't have a real meaning for us. So how do we balance the two constraints? Well, we're going to use a statistical measure called TF-IDF, so term frequency inverse document frequency. So this is a value that we're going to compute. It is a measure that helps in reflecting how important a word is to a specific document. So we compute it by multiplying two terms, the TF term and the IDF term. So what do these terms mean? So basically the first term is the frequency of a certain word T in a certain document. So this we compute it as a raw frequency, so just a count. So this is the formula that you see here. So count TD is basically count the number of times this word appear in a certain document. Now we use the log in that case because we want to squash the values on a smaller scale, because the fact that a certain word appears 100 times in a document does not mean that it's 100 times more likely to be specific to that document. So we just use the logarithm to squash the values on a lower scale. And we add the +1 because if the count value is 0, well, the log function is not defined on 0. So we add the +1 and log of 1 is basically 0. The second term is the inverse document frequency. So it's going to give a higher weight to the words that occur only in a few documents. And the formula is right below. So N in that case is the total number of documents across the entire corpus. And the DF term, the document frequency term, is the number of documents in which the term T occurs. So basically the intuition behind this is that if that word appears only in a few documents, this value, IDF, is going to be big, which means that this value, which is the TF IDF value, is going to be big as well. So this word is going to have some importance. It's going to be meaningful to us. If a certain word appears too many times, it appears, let's say, across all the documents. So this value is basically going to be N. And that N over N is going to be 1, and this term is going to be 0. So the TF IDF value for that word that appears in all the document is going to be 0 as well, which tells us that it's not important. So just to show you visually, to make it more clear, if you look at the co-occurrence matrix, we see for the word good, for example, it appears many, many times in many different documents. That basically tells us that this is not really relevant. It's just something that is not going to give us more information. So when we apply TF-IDF, we see that good goes to 0, basically because it appears in every document. So the inverse document frequency term is going to be 0, and the total TF-IDF term is going to be 0 as well. Now, everything that we mentioned, the co-occurrence matrix that form the vectors and the TF-IDF, there are two problems with this. Those are long vectors and sparse vectors. Long vectors because they span the entire set of words for the entire vocabulary, and sometimes the vocabulary is of size 30,000. So you're going to end up with a word vectors that is of length 30,000. So this is very long. And they're sparse because that means basically that most of the elements in that vector is 0. So because it's highly likely that some words never appear, never co-occur. So how do we mitigate this? There's an alternative, and basically we use dense embeddings. So the goal is to learn a vector that is short. That means the length is much smaller than 30,000. And basically it can go from 100 to, let's say, 1,000 values, and is dense in the sense that most elements are non-zero. So why do we do this? Basically, we realize that in practice it works better. So since they're shorter in terms of length, and the number of elements correspond to number of features, when we train a model, that means that we would have less parameters to tune, when we train the model, and this will help us generalize better and thus have a model that is more that is better at generalizing and making predictions. So there's one of the most popular uh, algorithm for learning dense vectors, and that is word2vec. So the idea is simple. Instead of counting how frequently a certain word is going to appear in certain documents, we're going to turn this problem into a binary classification task. So the goal is to be able to classify whether two words are neighbors. That means they share the same context. That means they are next to each other in a text. So the classification per se does not matter, but while we train this algorithm, the weights associated, the parameters associated to that training are going to be used as the embeddings. So I'm not going to go in all of the details because it would take too much time, but I have added the reference here. I highly recommend to go over this. It will give you a lot more intuition on what is word embeddings and how word2vec is implemented. I will just give a high level overview of the training process. So when we train word2vec, we start basically by initializing two matrices, an embedding matrix and a context matrix. Both matrices have the same dimensions. That is, along the rows, we have the size of the vocabulary. So that is all the words that span the entire documents. And we have the embedding size. And the embedding size is something that we choose. So if we want our dense vector to be 100 values long, then we choose 100. It can be 300, it could be 500. We'll see after why we need an embedding and a context matrix. So once we train, we have the data set. Remember, this is the embedding matrix and the context matrix, and we have our data set. And the goal, as I was saying earlier, is to be able to predict whether two words are neighbors. So what we see here, for every row, we have an input word, which we're going to call the target word, and an output word. Those are words that appear in documents, right? And remember what we mentioned about windows. We can take a window of a certain elements, and then we can see if words are considered as neighbors or not. The target tells us basically, because this is a self-supervised learning task, the target tells us whether the two words are neighbors or not. So whenever the value is 1, that means that those words are neighbors. If it's 0, that means that they are not neighbors. So the goal is to train a classifier that will be able to predict whether two words are neighbors. And so how do we do this? So every time we need to make a prediction for a certain observation, a certain row, what we're going to do is we're going to look up the embedding for the specific word, which is our target word. In that case, it's not. And then the words that we want to see if they are neighbors or not, we're going to fetch them, their embedding, from the context matrix. So we have the embedding for our input word, the target word, and the one for the potential neighbor words. And so what do we do after? We're going to compute the similarity between the input word and each output word. And basically, we do that using the dot product, and the higher, which is basically an element-wise multiplication of each element of each vector. They have the same length, remember? And the higher the value, the more similar they are to each other, and the more likely they are to be neighbors. So since it's a self-supervised learning task, we have the error rate, and this error rate is what we're going to use to update the values of our embeddings for the embedding matrix and the context matrix. So we're going to do that repetitively until our classifier is trained, and we're going to use the result of those embeddings, of those weight, of those parameters, as the embeddings for the words in that specific document. So this is just a concrete example of how it can be applied. Let's say we take it in the context of a language modeling task, which is basically being able to predict the next word when we input a few words. So let's say we pass those shalt, and we want to be able to predict what would be the next word. So this would be the process. We're going to look up the embeddings, make the prediction, and see which word is more likely. So this is exactly the situation where we're going to use the embeddings that we have trained, remember, as part of the word2vec algorithm. Once the training is done, we use that embeddings matrix to fetch the embeddings associated to each word. And then for all the words, we're going to grab the embedding, and we can either concatenate them or take the average value and use that as an input to a classifier that is going to predict what should be the next word. In that case, we see that it should be not. Sorry, guys, I'm going a bit fast. I'm trying to go over everything. So we talked a lot about word embeddings, and Ilham mentioned that we have word embeddings, but we also have sentence embeddings. And remember, a word embedding is basically going to capture the meaning of a word based on its context and is going to represent it as a numerical vector. However, it's also possible to represent a sentence, which is basically just a sequence of words by a numerical vector. So in a similar way to word embeddings, the sentence embedding is going to represent a sequence of words as a numerical vector. So we can train, for example, a language model, as we saw in the previous slides, and basically it's going to take as inputs a sequence of words, and every word is going to have an embedding associated to it. So essentially it takes as input a sequence of word embeddings, and is gonna apply those embeddings, and is going to create a unique vector for that sequence of embeddings, and that unique vector is going to represent the meaning of that sentence specifically. So the same way we have word embeddings, we can have sentence embeddings. And one method, one approach that is popular, and basically that is an extension of Word2Vec, is a model called Doc2Vec, which is basically trained a bit differently than Word2Vec, but essentially it uses the same intuition. So the goal is to generate a representation, an embedding for pieces of text that are of varying length. So we can have sentences with 10 tokens, 10 words, some other with 500. So whether it's for a sentence, a paragraph, or a document, it's going to be able to generate an embedding for that sequence of words. And so I put here a few links for the readings. I would once again highly recommend to go over the link by JLMR, so the Illustrated Word2Vec. This will give you a lot of intuition about word embeddings and tell you much more details how Word2Vec is implemented. And I put references to Doc2Vec. So the second point is basically the paper associated, the research papers, or if you're feeling adventurous and want to have a go at it, well, feel free to go through it and try to understand it. That was it for my presentation. I also had a quick notebook prepared. I don't know if I have a bit of time, Monica.
Actually, no. Do you want to share it on Slack?
Okay, I can do this. I'll just share the notebook on Slack, and you guys can go through it. It's not too difficult, and there's going to be an assignment with all the guidelines explained, so you should be able to understand it.
Thank you so much, Mo and Elham. Was very useful.